Welcome to this explainer. Okay, I am absolutely thrilled you're joining me today because we are going to look at something truly fascinating. We're going to explore a mind-bending mathematical magic trick that honestly completely defies human intuition. It's formally known as the Pigeonhole Principle. Specifically, we're covering chapter 5.3 of our source material today, and it proves how we can actually guarantee certain outcomes without even knowing all the facts. All right, to set the stage here, I want you to visualize a very specific scenario. Imagine you walk into a huge room, and this room is packed with exactly 367 completely random strangers. You don't know a single thing about them. You haven't spoken to anyone. Here is the crazy part. Without asking a single person in that room for their birthday, we can mathematically guarantee, with absolute 100% certainty, that at least two people in that room were born on the exact same day. It feels like a magic trick, right? And it begs the ultimate question. How can absolute certainty exist without any prior data? How can we know something for sure without even checking? To figure that out, let's look at Section 1, the basic mathematical blueprint. To unmask this trick and move past just chaotic guesswork, we have to examine the foundational math. Here is the formal rule, laid out in Theorem 1. We have a function, we'll call it f, that maps items from a domain to a range. Our domain, the inputs, is represented by the letter n. Our range, the possible outputs or categories, is represented by m. The theorem basically states that if this function is not a one-to-one perfect match, then the available outputs, m, are strictly less than the inputs, n. And this brilliantly illustrates what that theorem actually means in practice. Over in set A, our domain, we have n equals 4 inputs, represented by those blue dots. In set B, our range, we only have m equals 3 available outputs, those little squares. If you draw lines connecting every single dot to a square, well, because 4 is greater than 3, you are completely mathematically forced to have a collision. That bottom square highlighted in orange absolutely must receive more than one input. There's simply nowhere else for that fourth dot to go. Now, let's translate that super strict formal rule into a much more intuitive core metaphor, which, you guessed it, is where the principle gets its famous name. Think of your inputs, your n elements, as pigeons, and think of your available categories, your m elements, as pigeonholes. The principle states it simply. If you have more pigeons than pigeonholes, so n is greater than m, then at least one pigeonhole must contain two or more pigeons. It is just unavoidable structural logic. So, applying a simple three-step rhythm to that starting riddle reveals the magic. Step 1, identify your variables. Our 367 people are the pigeons, Rn. The 366 possible days in a leap year are the pigeonholes, Rm. Step 2, apply the blueprint. Is n greater than m? Yes, 367 is strictly greater than 366. And because of this, step 3 activates, the deduction. The principle guarantees a collision. Without a shadow of a doubt, at least two people share the exact same birthday. We use this exact same logical blueprint for things like exam marks too. Suppose we want to figure out how many students we need in a class to ensure at least two get the exact same mark on a standard 0 to 100 scale. First, identify m. From 0 to 100 inclusive, there are actually 101 possible marks. Those are our pigeonholes. To force a collision where n is greater than m, while the lowest integer strictly greater than 101 is 102. So logically, we need at least 102 students to guarantee that two share a score. Moving on to Section 2, scaling up the principle. Okay, that covers the basics, but what happens when we drastically raise the stakes and assign massive numbers of items to tiny, limited categories? The fundamental rule tells us a collision will happen, sure, guaranteeing at least two items share a category. But if we have a massive flock of pigeons and just, say, 3 tiny pigeonholes, surely some holes will end up with way more than just 2 pigeons, right? To handle this, we can't just guess. We need a brand new mathematical tool to calculate the exact minimum collision size. Enter the floor function. You'll see it represented by these special brackets with the little feet at the bottom. This is a simple but incredibly powerful rule where you must always round down to the nearest whole integer. On a standard number line, if you have 3 divided by 2, which is 1.5, the floor function pulls it straight down to 1. 9 divided by 4 is 2.25. That rounds down to 2. It literally just anchors the number down, and it's essential for our next formula. Which brings us to Section 3, the extended pigeonhole formula. With the floor function secured in our toolkit, we can build out the ultimate structural framework. The crucial point is this completed formula, the extended pigeonhole principle. It states that one pigeonhole must have at least the floor of n-1 divided by m, all plus 1. We can read the anatomy of this pretty easily. N is still our total pigeons, m is our total pigeonholes. We subtract 1 from n, divide by m, apply our floor function to round down, and then finally add 1 outside those brackets. That plus 1, that is the collision guarantee. It's the final pigeon. It crosses the threshold and forces the mathematical overlap, no matter how massive the numbers get. Let's run our initial 367-person birthday scenario through this upgraded formula just to see it in action. Our n is 367. Our m is 366. We plug them into the formula, the floor of 367 minus 1 over 366 plus 1. That simplifies to the floor of 366 over 366 plus 1. Now, 366 divided by 366 is exactly 1. The floor of 1 is just 1. Add the 1 on the outside, and you get 2. Exactly 2 people are guaranteed to be in one pigeonhole. All right, Section 4, Reverse Engineering and Challenges. Now that we have the formula, let's flip the script. In the real world, you usually know the outcome you want, and you have to build the system to guarantee it. So we can reverse engineer the problem to find our starting inputs instead. Applying this reverse engineering to exam marks, let's say our target collision is 2 students. That's our answer. Our pigeonholes, m, are the 101 possible marks. We need to find n. We set the whole formula equal to 2. To make the result 2, the floor function part must equal 1, working completely backwards. n-1 divided by 101 equals 1. Multiply both sides by 101, and you get n-1 equals 101. Add 1, and the formula algebraically proves we need exactly 102 people to begin with. Okay, pop quiz time. Let's see if we can do this on the fly. Here is Mastery Challenge 01. If there are 30 students in a class, how do we use the extended pigeonhole principle to mathematically show that at least 2 of them have names starting with the same letter of the alphabet? How do we plug this in? Take a second. Can you spot the variables? Our pigeons, the items being distributed, are the students, so n is 30. Our pigeonholes, the available categories, are the letters of the alphabet. There are 26 letters, so m is 26. Plug it in, 30 minus 1 is 29. 29 divided by 26 is 1 point something. The floor function pulls that right down to 1. Add the 1 on the outside and you get 2. Boom! 2 students are guaranteed to share a starting letter. All right, ready for the final boss challenge of this explainer? For Mastery Challenge 02, we need to figure out how many students are needed in a class to ensure that at least 6 students get the exact same grade, given there are only 5 possible letter grades, A, B, C, D, and F. Reverse engineering this one is actually really fun. Our target overlap is 6. Our M, the possible grades, is 5. We need N, so the whole formula equals 6. That means the floor function part must equal 5, right? Because 5 plus 1 is 6. So n-1 divided by 5 equals 5. Multiply both sides by 5. n-1 equals 25. Add 1 to both sides, and it reveals we need exactly 26 students to mathematically force that specific outcome. It works perfectly every single time. And finally, Section 5, From Chaos to Certainty. As we wrap up this explainer, let's just zoom out for a second. We've done a lot of math today, but I really want us to look at the profound, almost philosophical truth we've just uncovered. Think about this journey. We start with pure chaos, a totally disorganized cloud of data points. But by identifying those raw inputs, your n pigeons and m holes, and applying a rigorous mathematical blueprint, we extract undeniable deductive truths. We literally pulled absolute certainty out of wildly incomplete information. I really want to leave you with this powerful summary. Absolute certainty is a function of structure, not observation. We didn't have to observe every single birthday or grade or name to know the outcome. The structure itself guaranteed it. So I want you to think about this as you go about your week. If math can guarantee certainty without ever checking the data, what other invisible structures are silently dictating the outcomes of the chaotic world around you right now? Thanks for joining me on this explainer. Keep asking questions, and I'll catch you next time.